Imagine that you are a manager of a famous music company, and you want to predict how many albums your company can sell in the first week after release. What kind of statistical procedure will you use to help you answer this question? In this tutorial, we will learn about the statistical procedure that helps you make a prediction based on available data. Hello everyone, today I will walk you through the concept and JASP procedures of simple linear regression. I will start off by introducing you to simple linear regression. Then, I will show you how to run simple regression in JASP. If you have a handout, this procedure is on pages 26 to 39. I will conclude this tutorial with an example of APA write-up of the JASP results. When talking about relationships, I want you to think about correlation. In comparison, when talking about predictions, I want you to think about regression. Regression is a predictive analysis. It is used to predict an outcome variable based on predictor variables. Regression allows us to mathematically model the relationship between two or more variables using simple algebra. In simple regression, we will deal with only two variables, predictor variable, or independent variable, and outcome variable, or dependent variable. When we say our regression model is good, we usually compare the model with another specific model. We will talk about that as we go. Regression is a very flexible method. As you might have seen that there are many types of regression. For pedagogical purposes, I will use the simplest way to differentiate them. If your data are measured on continuous scales such as interval and ratio, and the relationships between dependent and independent variables are linear, you will likely conduct linear regression. That being said, the assumption of parametric regression must be met. If you have only one predictor, you are doing simple regression. On the other hand, if you have several predictor variables, you are doing multiple regression. If your data are nominal or ordinal, you may do logistic regression and ordinal regression, respectively. However, there are so many regression methods out there. It is out of the scope for this tutorial, so we will keep it for later. As this tutorial will focus on simple linear regression, please be mindful that from now on, when I say regression model, I mean simple linear regression, as opposed to multiple regression and nonlinear relationship. The difference between simple and multiple regression is that the number of predictor variables your regression model has. For example, if you want to predict the number of album sales based on one variable, that is, airplay, or the number of songs in the album are played on a prominent national radio, you are doing a simple regression. In comparison, if we want to predict the sale based on three variables, namely the number of times songs played on national radio, the budget spent on advertising the album, and the band's attractiveness, we use multiple regression. Generally speaking, regression can be used for several reasons. When you do correlation and find out the variables are associated, you may want to do regression to further determine the magnitude of relationship between independent and dependent variables. Regression allows you to quantify the individual or combined influence of predictor variables on the outcome. Thus you can use that mathematical relationship to predict change in outcome, such as predicting album sales based on airplay. When you develop regression model to predict a future or real-world phenomenon, you will examine how good your model is. That is how precise your prediction is. For example, if you use your regression model to predict that a company will sell about 1 million albums 1 week after the album release. In reality, you find that 990,000 albums are sold 1 week after the album has actually been released. Your prediction is pretty close. In comparison, if the actual sale is 100,000 albums, your prediction is much far from the real world. Hence your model is not effective. You can also improve the existing regression model from previous research. In such case, you would add more variables to the model progressively using some methods, such as hierarchical or sequential regression. For example, someone might use the number of times songs are played on the national radio and budget on the advertisement to predict the number of albums sold. You might add one more variable, such as the number of followers on social media the band has to that existing model. Next, let's get into deeper concept of simple linear regression. Okay, please be informed that I make up this data to describe how you might create a regression model. Imagine that you are a manager of a famous music company, and you want to predict how many albums your company will sell in the first week after release. You want to develop a model that helps you predict the number of albums sold in the future 1 week after your company releases the new album. So, you collect the data of the sales of 6 albums. For example, Album 1 has a sale of 350,000 albums, whereas Album 2 has a sale of 100,000 albums. Based on this data, I would like to challenge you on how you will make a prediction. I always like to use visuals to explain abstract concepts, and hopefully, I can help you understand regression better. So, let's start by visualizing our data. Let's put our data into the graph of album sales. Now, the x-axis is album number, which is not really the variable, and it is just a describer of which album we are graphing. And the y-axis is a vertical axis that where we'll graph the number of albums sold. Let's go ahead and see what this look like. For album 1, we have a sale of 350,000 albums. For album 2, we have the album sale of 100,000, the point will be down here. For album 3, we have a sale of 250,000 albums, we plot the point here. For album 4, we have a sale of 200,000 albums, we plot it here. For album 5, we have a sale of 450. We plot it up here. And finally, for album 6, we have a sale of 300,000, we plot the data point here. These are the data points, but please remember that we are now dealing with only one variable, that is album sales. The sales alongside the bottom just describe where we are graphing the sales. The position order doesn't matter, as we could have graphed any album in any order. So how would you predict the sale for album number 7? What is your best guess? Is it going to be the same as album number 6, which is 300,000 albums will be sold? Is it going to be the same as album 2, which is 100,000 albums will be sold? Well, your best bet would be the mean. The average number of albums sold is equal to 275,000 albums. That is the best we can do. So, if we know only one variable, the best predictor, our best estimate would be the mean. So, for any given album, our best guess for its sale would be the mean, equal to 275,000 albums. The mean is our best predictor if we know only one variable. Let me state this again, if we know only one variable, our best prediction for the sale of album number 7 would be the mean of 275,000 albums. However, as you can see that none of the album sales is equal to the mean of 275,000. All data are scattered around the mean actually. Deviance is the difference between each data point to the y-bar, or a mean of sales is called residual or error. You may remember from our previous tutorials on variability in week 2 and using the mean as a statistical model in week 4. I bet you also remember that the sum of deviance will away equal 0. To avoid that, we will square each deviance and sum them up. We will get a value called sum of squared error, or SSE, or the total sum of squares, or SST. With a small calculation, we get our total sum of squares equals 73,750. Simple linear regression aims to create a linear model that minimizes the total sum of squared errors. We want to create a line, aka regression model, that fits the data points better than the mean line. If our model is significant, it will eat up the differences between the line and data points. That means we want the line that has the least distance to every data point as possible. The regression line should literally fit the data better because it minimizes the residuals or errors. To sum up, when conducting simple linear regression with two variables, we will examine how good the line fits the data by comparing it to the fit of data to the mean. Okay, now you have some grounding of simple linear regression. That is, Simple linear regression is a comparison of two models. One is where the predictor variable doesn't even exist, while another uses the best fit regression line. If you have only one variable, the best predictor for other values is the means of the dependent variable. For example, if you know only the number of album sales, the mean of the sales is your best estimate. If you know two variables, one is dependent while another is independent variable, you can create a model regression using the best fit regression line. You will compare the two variable model with the one variable model, or the model with the mean. That is, you will compare a simple regression model to the mean alone. To determine if your model is good or not, you will consider how your regression line fits the data. The difference between the best fit line and the observed value is called the residual or error. You want the total sum of residuals or errors to be as little as possible. Now, suppose we happen to know one more variable, airplay. We want to predict the sale of albums based on the number of songs from albums being played on a prominent national radio the week before release. We will create simple regression based on these two variables, sales and airplay. To give you a clear picture, let's make a scatterplot of sales and airplay. Sales is dependent variable, so we will put it on the y-axis, whereas airplay is our predictor, we will put it on the x-axis. For album number 1, songs are played 100 times, and 350,000 albums are sold, so we mark our data point here. A radio station plays songs in the album number 220 times, and 100,000 albums are sold, so we put the data point here. For album number 3, songs are played 60 times, and 250,000 albums are sold, so we graph the data point here. We do the same for other albums. Now suppose we create a regression model y hat equals beta sub 1 time x plus beta sub 0, and get the regression line like this. Beta sub 1 is a slope of regression model. It tells us how much sales will change when airplay change in a certain amount. Beta sub 0 is the y-intercept, and it tells us where the regression line cross y-axis. This will happen when airplay is 0. That means it is a point that shows the number of albums sold when a radio station doesn't play any song in the album at all. The purple dots represent predicted values. They are calculated based on regression model, while the red dots represent observed values. They are the values we obtain in the real world, that is, they are the values we collected in the first place. The difference between the predicted value and the observed value is called residual or error. If the residual is big, it means our prediction is far from reality. If our residual or error is small, it means our prediction is close to reality. If we add up all residuals or errors, we will always end up with 0. So we need to square each residual and add them up. The product of adding up squared residuals is called sum of squared residuals or SSR. Again, with a small calculation, we get the SSR as 1750. We want the sum of squared residuals to be small as possible. We want to compare our regression line to the mean in terms of which one has less sum of squared errors. As you can see, that total sum of squared, which represents the error due to using the mean as a model, is bigger than residual sum of squared. Hence, we can see that regression model is a better predictor than the mean of album sales. There is another concept I want to talk about in this tutorial. If we measure a distance from the mean of album sale to regression model, square each distance and add them up, we will get something called the model sum of square, or SSM. What is SSM then, you may ask? Well, SSM is the sum of squared due to regression. Regression eats up these errors of using the mean as a predictor. That is, SSM plus SSR will equal SST. If we divide SSM by SST, we will get R squared, which is a very important term for correlation and regression. R squared tells you how much variance in the dependent variable is explained by independent variable, or a predictor. For example, we get our R squared as 0.98 from the calculation. We can say something like 98% of variability in album sales is explained by variability in the number of times songs in the album are played on a national radio. Please be mindful this is made-up data for pedagogical purpose. In the real world, it is very unlikely to get a simple linear regression model that has this very high R-squared. Let's speed things up. From behind-the-scene calculation, we get our model as y hat equal 2.5x plus 70. Don't worry, JASP will calculate these numbers for you. The number 2.5 is beta sub 1. It tells us that if a national radio plays songs in the album 2.5 more times, a music company will sell about 1,000 albums more. The bigger the beta sub 1, the stronger the relationship between predictor variable and outcome variable. Number 70 is beta sub 0. It tells us that if a national radio doesn't play songs in the album at all, airplay equals 0, a music company will sell about 70,000 albums. Okay, enough with theory. Now it is time to perform regression with real data. We will use built-in data in the JASP library. This dataset is from Field, and we are grateful for his generosity in sharing it with us. We will do simple linear regression in JASP and practice writing up a report using APA style. Our task is to predict album sales based on the number of times songs in the album are played on national radio or airplay. To open this dataset, go to the main menu, hit Open and click Data Library. Next, choose Categories, then Regression and Album Sales. If you click the first option, you are opening the JASP file, and you will find that someone already does regression for you. If you want to see how regression is done with some explanation, you can choose this option. However, for today we will do it ourselves, so please choose the second option, which is the data file. Once you open the dataset, you will see this window. I think it is helpful to understand data before we do any analysis. So, let's take some time talking about it. First, as you can see that we have 4 variables here: adverts, sales, airplay, and attract. So, let's make more sense of what they are and how they are measured. Adverts represents the amount of money spent on advertisement of the album in thousands of British pounds. So, for example, the 10.256 here means the company spends about £10,256 on advertising this album. Sales represents the number of albums sold, in thousands. For example, the 330 here means 330,000 albums are sold the first week after release. Airplay represents the number of times songs from the album are played on the national radio the week before release. For example, the number 43 indicates songs in this album are played on the radio 43 times a week before release. Attract represents activeness of the band. The mode of attractiveness ratings from 0 to 10, when 0 indicates low attractiveness, and 10 shows high attractiveness. For example, the 10 here represents this band as highly attractive. For album number 1, they spend £10,256,000. The songs in this album are played on the radio 43 times the week before release, and this album is rated 10 out of 10. The company finds that 330,000 albums are sold the first week after release. They do the same to album 2, album 3, and so on. They get 4 pieces of information for 200 albums. Our task today is to use this information to predict album sales. Based on this dataset, we want to predict how many albums will be sold the first week after release. Now, we have some understanding of the variables. Let's make sense of our task. We want to help a company manager predict the number of albums sold based on these variables. If we choose one of these variables as a predictor variable, we will do simple regression. If we add more variables to our model, let's say all of these, adverts, airplay and attract, we will do multiple regression. However, for this tutorial, we will start with a baby step. We will do simple regression. To be more specific, we will create a simple linear regression model which consists of one predictor variable, and one outcome variable. We will use the number of songs that are played on the radio a week before release to predict the number of albums sold. But let's get back to simple linear regression model. A simple linear regression model is an equation that shows the relationship between two variables. Y hat equals beta sub 1 multiply x plus beta sub 0. When y represents an outcome variable, and x represents a predictor variable, beta sub 1 is known as the beta coefficient. It is a slope of regression, which tells us how many an outcome variable will change concerning a 1-unit change in a predictor variable. And beta sub 0 is an intercept of y when x is equal to 0. To visualize our model, we can spell the model out as album sales equal to beta sub 1 multiply airplay plus beta sub 0. Let's look at each element in our model. Beta sub 1 quantifies the relationship between album sales and airplay. Beta coefficient, or regression coefficient, tells us how many albums sold will increase if we increase the airplay by 1 unit. In comparison, beta sub 0 is a y-intercept that tells us where the model is when airplay equals 0. In other words, how many albums will be sold if a national radio station doesn't play any song in the album at all. It may seem so abstract for you right now, but I promise it will make more sense later. We are doing simple linear regression to find out two values, beta sub 1 and beta sub 0, so that we can use airplay to predict album sales. Here is the workflow for simple regression. Step 1, we will select the appropriate statistic. We would like to know if the number of times songs from the album are played on the radio the week before release predicts the number of albums sold. Therefore, we conduct a simple regression. Step 2, we identify the null and the alternative analysis as follows. Our null hypothesis is that the beta coefficient equals 0. In other words, the regression coefficient is 0. For the layperson, we can say that our null hypothesis states that changes in the number of songs in the albums are played on the radio doesn't affect the number of albums sold. In other words, regardless of how many times the radio station played songs in the albums, the number of albums sold the first week after release stayed the same. In contrast, our research hypothesis is that the beta coefficient does not equal 0. This means the number of songs played on the radio affect the number of albums sold statistically significantly. Step 3, we select a level of significance we want. However, today we will do a two-tailed test at a significant level of 0.05. Step 4, we will calculate the statistic. We will firstly test assumptions for simple linear regression analysis. Then, if the assumptions are met, we will perform simple regression analysis. Step 5, we will decide whether or not we will reject the null hypothesis and write an APA-style report about our statistical procedure. We have decided to do simple linear regression at a significance level of 0.05. We have identified our null and alternative hypotheses. Now let's move to step 4, test assumptions followed by calculate statistics. There are 4 main assumptions for simple regression. Firstly, outcome variable follows normal distribution. Secondly, the relationship between outcome variable and predictor variable is linear. Thirdly, all of the values of the outcome variable are independent. And lastly, the variance of predictor variable and outcome variable should be the same. There should not be extreme outliers in our data, because regression is sensitive to outliers. Let's check each assumption one by one. As we learned from the previous session, that there are several ways to look at normality. You can do a descriptive statistic here to look at z-values of skewness and kurtosis and the Shapiro-Wilk test. You can look at QQ plots, histograms and box plots to evaluate normality. I will not go on in detail, but you can look at the previous week handouts for more information. Instead, we will look at the following assumptions: linearity and homoscedasticity. We want to test if sales and airplay are linearly related. From the scatterplot, we also can examine if the variance of the error term in a regression model is constant. If the variance of the error term is homoscedastic, our model is well defined. To do that, we will click on regression, then classical, then correlation. Next, move sales and airplay to variables. In the sample correlation coefficient pane, tick Pearson's R and scatter plots. According to the scatter plot, the more songs the album has been played on the radio the week before release, the higher the album sales. We can see that the sales and airplay variables form the linear line. That is to say, they are linearly related. Additionally, the spreads of data above and below the regression line are approximately similar. In other words, we have homoscedasticity. Homoscedasticity means having the same scatter. For it to exist in a dataset, the points must be about the same distance from the line, as shown here. The opposite is heteroscedasticity, referring to different scatter, where points are at widely varying distances from the regression line. Please be mindful that I said distance here, not variance. It is easier to look at the distances from the points to the line to determine if a data set displays homoscedasticity. We can also test the pairwise normality by expanding the Assumption Checks tab and tick Shapiro under pairwise normality. The results are shown under the assumption check. If the p-value of Shapiro Wilk test for bivariate normality is greater than 0.05, the bivariate distribution is normal. We get the p-value for Shapiro Wilk test for bivariate normality of 0.459, which is greater than 0.05. So we conclude that bivariates between sales and airplay are normally distributed. We will check other assumptions as we do simple linear regression. To do that, go to regression, then classical, then linear regression. The next step, move sales to dependent variables. We will set method as enter for this exercise. Then, move airplay to covariates. Before performing linear regression, we need to check more assumptions, such as the outliers and independence of observations. Expand the Statistics tab. Under Regression Coefficients, tick Estimate and set confidence intervals at 95.0%. Tick Model Fit and Descriptives, as we want this information for the write-up. To check if our data have extreme outliers under Residuals, tick Statistics. To check if all values of our dependent variable are independent, tick Durbin-Watson. Okay, now let's look at the results. According to the residual statistics table, the standard residual is equal to -2.717, which is in the range of -3.29 and 3.29 standard deviation. Hence, our data don't have extreme outliers. If the standard residual falls outside 3.29 standard deviation, we may need to exclude some extreme outliers. According to the model summary table, the Durbin-Watson statistic for the null and alternative hypotheses are equal to 1.807 and 1.907, which are in the range of 1 to 3. Hence, the assumption of independence of observations has been met too. If the Durbin-Watson statistic falls outside 1 to 3, it indicates that all values of outcome variables are not independent, and we may use more robust methods such as bootstrapping. We can check the assumptions of normality and homogeneity of variance and outliers by expanding the Plots tab. Under Residual Plots, tick Residual vs predicted. The residuals should be randomly scattered across the whole graph around the baseline. We will inspect that in a minute. Next, tick Residual vs histogram to check the outliers. The residuals should fall within -3 to 3. To check normality, tick QQ plot standardized residuals. The dots should align with the diagonal line in the QQ plot. Let's inspect these assumptions. According to the residuals plots of residual versus predicted, the residuals are randomly scattered across the whole graph around the baseline. This indicates our data have the same variance. Thus the assumption of homogeneity of variance has been met. According to the residuals plots of residual versus histogram, standardized residuals, our residuals fall within -3 to 3. Hence there are no outliers. Now we can conclude that 1. Our dependent variable, namely sale, follows normal distribution. 2. The relationship between sales and airplay is linear. 3. All of the values of sales are independent. And 4. The variance of sales and airplay are the same. Hence, all assumptions of simple linear regression have been met. Now, it is time to interpret the result. First, let's look at the model summary table. Here, I want you to look at R and R squared. If you can recall, that R is the correlation coefficient. We can interpret the R square, or coefficient of determination, as the effect size of correlation, and we can interpret it like this. We have the R squared of 0.359. We can say that 35.9% of variation in album sales is explained by the number of times songs in the album are played on the radio. There is a statistically significant relationship between our predictor and the outcome variable. Airplay is a predictor of album sales. If this ANOVA is not significant, then airplay doesn't contribute to predicting the number of albums sold any better than using the mean of sales, or the y-intercept. ANOVA is another way we look at our regression model. The ANOVA table tells us that the model works. If the p-value of the f-test is less than 0.05, our regression works well. In layperson terms, we can say that number of times songs in the album are played on the radio predicts the number of albums sold better than using the mean of the sale to predict the sales. Before we talk about coefficients, I want to talk about descriptive statistics, as we will use this information in the write-up. We know the mean and standard deviation for each variable. We know that data of 200 albums are included in this data set. Let's move to a very important part of regression analysis, the coefficients. While ANOVA tells us if the model works or not, the coefficients table tells us how the model works. This table will help us find the beta coefficient, or beta sub 1, and y-intercept, or beta sub 0. There are two kinds of coefficients, standardized and unstandardized. The standardized coefficient is equal to 0.599. Where have we seen this number before? Yes, it is the same number as correlation. And correlation coefficient is a standardized covariance. However, we want to focus on unstandardized coefficients. These values are still in the original units of measurement. That is, the number of album sales is still in 1,000 albums. The number of times songs are played on the radio still represents the number of times. For example, the number 193.200 here represent 193.2000 albums are sold, and it is not just a random number. Look at the descriptive statistics table, it is the mean of the sale. Just to let you know, that t-value is a square root of the f-value. If you take a square root of this f-value in ANOVA, 110.750, you will get 10.524, which is a t-value of a single predictor of sale. What I want to say is that all of these numbers tell us about our regression model in different ways. Now, it is time to find beta sub 1 and beta sub 0 for our model. Remember that beta sub 1 is the slope of the model, and beta sub 0 is the intercept of the y-axis. Although we don't see any labels for them directly, we can see them over here, in the coefficients table. The unstandardized coefficient for airplay is our beta sub 1, or beta coefficient. Our beta sub 1 is equal to 3.94. The unstandardized coefficient for the intercept of the alternative hypothesis is our beta sub 0, or the y-intercept. It is equal to 84.87. What I want you to look at is the t-value of our predictor, airplay. If the p-value for t-test of airplay is significant, as you can see, the p-value is lesser than 0.001, our predictor is significant in the model. On the other hand, if the t-test for any predictor is not significant, that predictor is not good. It doesn't improve the fit of the model. Look at the sign in front of our beta sub 1, is it positive or negative? No sign means a positive sign, and it indicates that airplay increases the album sales increase. In contrast, a negative sign indicates that if airplay increases, the sale will decrease. This is how we interpret the unstandardized beta coefficient, or our beta sub 1. For every 1 unit increase in the number of songs in the album are played on the national radio, album sales will increase by 3.94 units. Although there is no census format for reporting regression, one can write a report like this. However, please remember this is just an example. We firstly may describe that we use simple regression to predict album sales based on the number of times songs in the album are played on the radio the week before release. We may then talk about correlation, as we will do regression only when the predictor and outcome variables are related. Otherwise, there is no point to predict something based on something unrelated. In the next part, we can report and interpret the coefficient of determination, followed by an over-analysis and coefficients. Finally, we may mention the t-test in terms of the coefficient associated with our predictor, airplay. To predict album sales, we need to create our regression model. As stated earlier, our regression equation is y hat equals beta sub 1 x plus beta sub 0, or album sales equals beta sub 1 multiply airplay plus beta sub 0. We can plug in the number in the coefficients table to our regression model, and we get our regression equation as album sales equals 3.94 multiply airplay plus 84.87. Now, we will use the model to predict album sale. For example, imagine a recording company requesting a major national radio station to play songs in the album 100 times 1 week before release. Thus, album sales will equal 100 multiply 3.94 plus 84.87, which is equal to 478.87. Remember that the unit of album sale is in thousands. So, the company would estimate that album sales should be around 480,000 for the first week of sales. Now, you have learned about simple linear regression. The procedures I explain here are in the Week 7 handout on pages 26 to 39. I hope you have better understanding of simple regression. Specially thanks to Slides Carnival for this awesome PowerPoint template. And thank you for watching. I will see you next time.